This is Geometry Lesson 4.6, Translations as Vectors. So a big idea today is a translation can be described by a vector that gives its magnitude and direction. So just a reminder, translations are our slides where we take a figure or a point and we just move it somewhere. And so a vector is going to tell us how far to move it and what direction we can move it. So if you take a look at the picture, you've got the marching band on the field. And let's just say that the director wanted to move the entire marching band while still in formation down the field or shift them on the field. Every single one of these students, if we were going to keep this figure in its shape of the letter A, would have to march perfectly together the same amount of steps, either down the field, up the field, whatever. But if we think about every student as a point, every point in this figure is going to move the same exact distance, either up or down the field, left or right. And that is a translation. And the amount of steps that each one is going to take, let's say the director said, all of you are going to march exactly 25 steps forward and 2 steps left. All right, that will be given by what we're going to call a vector. So the definition of a vector is a quantity that can be characterized by its direction and magnitude. So we know what direction means, and magnitude is how much. So the vector is going to tell us which way to go, and magnitude represents how much. So in general, the magnitude of a vector is represented by its length, while the direction is determined by the direction of a ray. So you're going to actually see an arrow pointing for the direction. So the definition of a translation vector, and that's what we're going to be looking at, translations, is a vector that gives the length and direction of a particular translation. So you can see here we had this letter R represented by these points, and every single point is translated the same direction and the same amount, and then that gives us the image of R over here perfectly translated. Right? If any one of these points traveled a different direction or a different distance, we wouldn't have a perfect image over here to the right. And so the arrows in the diagrams above, and they're talking about these arrows right here, show 2 ways of identifying a translation vector. So we can look at it like this, and oftentimes this will come actually in the picture. So like if this was a shape and it had vertices that were labeled like A, B, and C, or something like that, they will describe the vector by a line segment that you actually see in the picture. We're going to move it this much, and it's actually the measurement of one of the sides or something like that. So very often you'll see that. So this actually tells you exactly how far this has moved. If we measured this, same with this one, okay, it's going to show you exactly how far this moved in the picture. Now, it's not just the length, it's also the direction. You can see these arrows are pointing the exact same direction as we moved every single one of these points. So the length of this line shows you how far the translation is going to go, and the direction points you the right way as well. So if we have it set up with the A and a B, the A is called your initial point and B is called your terminal point. You see this little half arrow, and they say it also could look like a harpoon. Above it, that's the symbol for a vector. So if we're going from a point to a point, you'll see it represented with AB and that vector symbol on top. Or sometimes it's just the arrow like this, labeled as a vector. All right, so example number 1. We're going to use this diagram to draw the image of triangle ABC under a translation, so a slide, given this vector. So we'll use, when we do these types of things, we'll use a ruler to try and get this as close as possible. But you could also kind of eye it a little bit. But this vector right here tells us exactly how far to move this shape. So if I measure this, this is exactly 3, and I'm measuring that there in millimeters. Okay, so every single point, A, B, and C, are all going to be moved that distance. And we also want to go that direction. We're not going to just move it anywhere we want. It's going up to the right like that. So when we do this, we're going to use the ruler to make sure that it moves 3, but I don't want to move it 3 this way or this way. All right, I want to go the same direction. So when I set this up, every single one of these directions should run parallel to this. So I'm going to line it up like this. And so like I could see, well, that's not parallel. That's not parallel. That's close, but not quite, right? So they should look like the two sides of railroad tracks as best as possible, right? That looks pretty parallel. And so I'm going to count up 1, 2, 3, and I'm going to draw this vector. You don't have to do this when we're actually doing it, but then my point is going to be right here, 1, 2, 3. So it moved a magnitude of 3 exactly in this direction. I ran parallel to that line to accomplish that goal. So that's going to be A prime, or the image of A. B, I'm going to do the same thing, try and get this looking parallel best as possible. And now I can also use this as a reference point, right? I can run parallel to that. And so 1, 2, 3. And that's going to be the image of B. And then the same thing for C, as best as possible. We're going to run this parallel to those. 1, 2, 3. And if I connect these, I should have a triangle that looks exactly the same as the original in terms of size and shape. And remember, under a translation, I'll go ahead and draw these vectors in here so we can see what we did. So we moved every point the same exact direction. And you can see this almost starts to make it look like a three-dimensional shape there when you connect them. So if I measured the side of AB, it should be pretty darn close to this. And under a translation, it would be exactly the same, because we know that the property of distance is going to hold true throughout this translation. It will be preserved. Same thing with angle measures. They should be exactly the same. All we've done is slid this amount in that direction. All right, now that can be a little tricky. You got to be kind of good with your ruler and eyeing up parallel lines and stuff like that. When we move this on a coordinate plane, it's much easier because we can just put numbers to it and use the graph or use the grid to do so. All right, so if you look in the picture, we've got C, D, E, H, the original, and then it's translated over here, C, D, E, H, the image of. Under this translation right here, this distance in this direction, that's the vector. So if you actually look at each one though, if I go to E and I go, all right, it went 1, 2, 3, 4, 5 to the right and 1, 2, 3 up. And if I do H, it went 1, 2, 3, 4, 5 to the right and 1, 2, 3 up. And if you look at this vector, it went 1, 2, 3, 4, 5 over, 1, 2, 3 up. So the vector has told you kind of the over and the up, a little bit like slope, of how to get from one to the other. So you could say that this is going to the right 5 units and then up 3 units. Now there's a way to symbolically do that besides just the arrow on the graph. So we're going to use these special set of brackets that look like this. So they're not curved, they're pointed like this. And that's going to represent your notation for a vector. So we went 5 to the right and then up 3. And so it kind of looks like a coordinate because this still represents like your x and your y. So this is what we're doing in terms of x. We're going to be adding 5. And then this is what we're doing in terms of y. We're adding 3, which makes it go up. And if these were negative, then we would go left and we would go down. So what this actually means is not just x and y. It's whatever x was, you're going to add 5 to it. And whatever y was, you're going to add 3 to it. That's what the vector is saying. So these are horizontal and vertical distance that we're going to move it on the graph. You've got your horizontal component and your vertical component of the vector. All right, so using that information now, let's go to example 2. So P prime is the image of the point P equals 3, negative 4 under a translation by this vector, negative 5, 8. So we're going to find the new coordinates of the image of P. So remember, this means take the x value and minus 5, and it means take the y value and add 8. So we're going to take 3 and minus 5. So my new value is going to be negative 2. And then we're going to take the y value of negative 4 and we're going to add 8. And so that is positive 4. So the coordinates of the image of P is negative 2, 4 under the translation by this vector. Pretty simple. And so example 3, suppose we have a translation. We went from Q to the image of Q, which was 4, 8, and became 1, 9. Find the vector that made this happen. So we're going to come up with the vector. So we went from 4 to 1. We went down 3. So that means the x value in the vector was negative 3. And we went from 8 to 9. We went up 1. And so that's just 1. All right, pretty straightforward. So to kind of wrap this up, we've now looked at 3 different types of transformations here in this chapter: reflections, rotations, and translations. So a reflection is like when we flip it, a rotation, we turn it, and a translation, we slide it. And a reflection is determined by wherever the line of reflection is, right? You flip it around over that line. A rotation is determined by a center and then how many degrees it's going to turn around it. And a translation, again, is a slide, and the vector tells us the direction and the magnitude. Now, all of these can be expressed as reflections or composites of reflections, like we've talked about. So a reflection is just one reflection over one line. A rotation is a composite of 2 reflections over intersecting lines. And a translation, we talked about, is a composite of 2 reflections over parallel lines. So if we flip twice over parallel lines, it's actually a translation. And if we flip twice over intersecting lines, that is a rotation.